Good morning, team. Are you ready to do exactly what we did in the last video on zero order reaction kinetics? Now we're going to do first order reaction kinetics. And gosh, I wonder what the next video is going to be. Zero, one, maybe second order reaction kinetics. We're just going to do the exact same thing as we did. We're going to, like I said, set up the rate law, look at what the rate actually is from that, from some generic equation. Do an integrate both sides, get an integrated rate law or integrated rate equation for first order reaction kinetics. And you're going to see it's quite different than for zeroth order reactions, and second order will be different from zero. So that difference from the integrations really gives us a lot of advantages in the little tricks we can do to figure out whether a reaction order is first, second, or third. For zero, first, or second. We're not going to do third and fourth on exams where you have to do that. We might run into them, but I'll make them where they're doable, right? You won't have to use integrated rate equations for them. And that's the meat and potatoes of kinetics, really, is, here's a problem. What order is the reaction? Is it zero, first, or second? That's always the first thing you're going to do. Look at the information provided. Is it zero, first, or second? And then you can go, okay, now I know if it's zero, first, or second order. I know what equation to use. Plug in the variables. I know what plots I can make. I know what the half-life. I'm going to do half-lives in a little bit. I know what the units are on the rate constant. Boom! Works out really nice. So following an exact same path. Oh, hold on. Got my hot tea. Yay. Where do you think it's tea? Okay. There's the evidence area. I'm a little tea bag there. It's really hot. We're doing a lot of kinetics videos today. All right, so let's take just like we did last time, a generic equation, right? A going to products, may or may not have some stoichiometric coefficient. Most of the time, the stoichiometric coefficient is going to be a 1, right? Especially for first order. Well, we can set up the rate law for that. So the rate will be the rate constant times the concentration of the reactant raised to the first power. In the last video, it was raised to the 0 power, which dropped that to a factor of 1, right? But now we've got this concentration that's going to create some issues for us. Well, we know rate is, since it's a reactant, negative 1 over the stoichiometric coefficient from the balanced equation times the change in the concentration of A final minus A initial, over the change in time, T final minus T initial. T initial is usually going to be 0. That'll equal the rate constant times the concentration. All right, well, we've got some changes going on to a chemist, or if you're in calculus, differentials. We've got delta A here and delta T. Let's move the delta T to the other side so we can get the time data on the right-hand side and the concentration data on the left-hand side. It's what we do every single time. So if I do that, I'm going to move the delta T over here. I'm going to move the coefficient A over there. I'm going to move the negative sign over there. And I'm going to move A over to the left because that falls under all the A stuff. So I'm going to end up with delta A over the concentration of A, or you could instead of dividing by the concentration of A, you could say multiplying by the concentration of A to the negative 1 power. I do that with units all the time. And so again, negative sign moves over, A moves over, delta T moves over. So delta A, the change in the concentration of the reactant, over concentration of A, is equal to negative AK delta T. And again, very commonly, many textbooks, many professors you have, they will not do any of this with that little letter A, with the assumption that the coefficient is equal to 1, which is pretty valid most of the time, right? So cool, one way or the other. Now we got the delta T on this side, or you calculus people, DT, or dx, whatever you want to call it, and we got the delta A on this side. So let's integrate both sides. So if you're in the next board, you don't have to know from my class. Well, I'm just going to give the equation. You don't have to know how the equation comes from the integration of this. But if you love math, if you love challenging yourself, or you're just generally bored right now and you like calculus, go ahead and integrate that and see if you can derive the integrated rate law equation for first order reactions. I'm going to pause this and pop it up on the board and see if we get the same thing. And again, if you're in calculus right now, it's more fresh in your brain than it was for mine. I think it was 32 or 33 years ago. I actually took my 3 semesters of calculus. Calc 1, 2, 3. Woo, those are some fun semesters. All right, let's hope I got everything up here correctly. Getting the calculus out of the brain here. So I rewrote the equation here. So delta A over A is equal to negative AK delta T. Integrate both sides. So we're going to integrate the left side from the initial concentration up to the concentration at time T. and this side from the time, from time t equals 0, the initial time, up to the final time, t. All right. Well, the right-hand side should look familiar because it's exactly the same as what we did for the 0th order reactions, and it'll be very similar to the 2nd order. It's just the left-hand side different, right? For 0 order, we didn't have this concentration in the term, right? It was just the delta A. So now this time we have delta A over A, which we can rewrite as A to the -1 times delta A, and I'm going to pull the constants out, the balanced stoichiometric coefficient, which is commonly just a 1 and left out, times K. So I pull the rate constant out. So you get the -AK, do the integral from 0 to T for delta T. So we've set it up. I'm just setting up here. Now you could do this either way, but if you are into calculus, and again, you don't need to know this for my class, we're doing this integral here. We're doing x to the -1 dx. Concentration to the -1, or 1 over the concentration. Same thing, right? Times delta A. So you can see the similarity. So you can look at that up on your integration tables and whatnot. And you'll see that you get natural logarithms. Ho ho! So when you do this integration, you get the natural logarithm of the concentration at time t minus the natural logarithm of the initial concentration. Hey, so log of AT minus log of A naught, and these are natural logs, will equal -AK, the constants, and this again will be T final minus T initial, but like in the last video, T initial is going to be 0, so it's just T minus 0, or just T, right? Boom, so -AKT. So I left that step out that I did last time. Now, there's two ways you'll see this first order, because first order is probably the most common one you're going to run into. 0th order, I don't run into very often, maybe for enzymes and things like that, but it's a little more biology. 2nd order, you can get a little more complicated. So first order, by far, is the most common thing. A lot of decomposition reactions are first order. If you go into nuclear chemistry, radioactive decay follows first order reaction kinetics. So you'll see this one quite a bit. Or we'll take a 2nd order reaction and make it into a pseudo first order reaction, so we can do this kind of stuff. So I can do one thing where, if you remember your stupid log tricks, right? Log of A minus log of B is just log of A divided by B, right? So a lot of times we'll go from this form to this form and back and forth. We do that a lot in 2nd semester of general chemistry. So I can just take log of AT minus log of A naught and make it log of AT over A naught, right? Okay, just kind of collapse them into one single log term, equals -AKT. This is going to be very useful if you're going to be solving for either the initial concentration or the final concentration, because you can just take e to the x on both sides and wipe out that logarithm term, right? So that's, in certain scenarios, like I said, solving for one of the concentrations, this will be the preferential form. Or we can just move log of the initial concentration over to the other side, just add it to both sides. So we get log of the final concentration, AT, is equal to -AKT plus log of A initial, right? So I just move the log of A initial to the other side. And this is useful if you're going to be solving for the time, right? The rate constant, something like that. Either one works, doesn't really matter, pick your poison. But this one I tend to use more when I'm doing example problems, or just problems in general. I do example problems, for first order reaction kinetics. This one I like to use when I'm looking at plotting concentration data versus time data and trying to get a straight line. Y equals mx plus b, because the initial concentration is a constant, right? So if I plot the natural log of the concentration on the y-axis and the time on the x-axis, I'll get a slope of -AK and a y-intercept of natural log of the initial concentration. Oh, we did that for 0 order, but we plotted just the concentration versus time. For first order, we got to plot the natural log of the concentration versus time in order to get a straight line. And we're going to find out that's one great way to determine if a reaction is first order. Plot the log of the concentration versus time. If you get a straight line, wada bing, wada boom. Another is to look at the units on the rate constant, which we're going to get from that plot. Let's do that on the next board. All right, so again, I provide these equations for you. Either this one or this one, doesn't matter, or this one. I mean, you can derive. If I give you this one, you can derive those two. If I give you this one, you can just split it up back to that and make that. You only need one of these three. All right, let's look at some plots. Yay, plots. All right, did you follow the exact same pattern we did last time? Just the exact same thing, right? The only difference is a slight little change on the left-hand side when we do the integration. And again, you don't have to know the integration. I'll just provide you the integrated rate equations on my quizzes and exams. So for first order reactions, this is the integrated rate equation in the form that gives you the y equals mx plus b. In the logarithm form, with the log of at over a naught, doesn't give you the y equals mx plus b. So if we plot on the y-axis the log of the concentration of that reactant versus on the x-axis the time, and that doesn't have to be seconds, it could be minutes, hours, days, millennia, whatever you want there. So y equals mx plus b. So m, the slope, will be the negative a times k. A being the stoichiometric coefficient from the Bell's equation, k being the rate constant. It's negative, so the slope should be negative. Commonly, a is going to be 1, right? So a lot of times they just say the slope is equal to negative k. The y-intercept will be the log of the initial concentration. So if you plot those, you should get a straight line. So that's one way you can check for first-order reaction behavior, is plot the log of the concentration versus time. If you get a straight line, wada bing, wada boom, you've got a first-order reaction. For zero order, it was the concentration versus the time to get a straight line. Very useful. It takes a while to do graphs by hand, but on Excel, you can type that data in, right? Make a graph, bloom. You can do a least squares fit. Bam, gives you the slope, gives you y-intercepts, piece of cake. You can get pretty fast. Do that in a couple minutes, actually. Boom. And what you can do is look at the different plots. Plot concentration versus time. See if you get a straight line. If not, plot the log of concentration versus time. See if you get a straight line. If not, we'll do it for the second order, which will be a little bit different. So again, y-intercept will be the natural log of the initial concentration when time equals 0, right? Slope, m, is equal to negative ak. Commonly, a is 1. So from this, we can get the units of the rate constant, right? So the rate constant is just the slope, right, which is delta y over delta x. Well, logarithm have no units. So it's the units on the rate constant will be no units in the numerator, right? And you've got time in the denominator. So you just, in this case, from this plot, it'd be 1 over seconds. But if you did this in minutes, it'd be 1 over minutes. If you did it in hours, 1 over hours, just inverse time. So that's a great way to do a little shortcut. If you're provided in a problem, remember the first thing you always have to do is what is the reaction order, 0, 1, or 2. If you're provided k, that's always an indicator of whether it's 0, first or second order. You just look at the units on the rate constant, right? Because if you're not provided in the problem that, hey, this is a 0 order, or this is first order, or this is second order, which is commonly given to you, but sometimes it's not. Going to make you think a little bit. So if it's not provided for you in the problem, you either have to do one of these plots to see if you get a straight line based on what the form of concentration you're plotting versus time, or look on the units of k. So if the units of k have no concentration units in it, it's just inverse time, whatever that time unit is, boom, first order. Remember, 0 order was concentration units over time units. Oh, I wonder if second order is going to be a little different than those. Hey. Well, let's do one problem of first order reaction kinetics. And we can either use this equation or the one where it's log of AT over A naught. Either one's going to give you the right answer. It's just a personal preference. So let's do an example problem. Ready for our example problem? Now, obviously, we're doing a video on first order reaction kinetics, but on an exam, you're not going to know when you just read a problem or in your homework or something. You're not going to know necessarily that's at 0th, first, or second order unless it's stated in the problem. All right, well, let's read this problem. First thing I look for, does it state if it's 0, first, or second order? If it doesn't, I go, oh, what a crap. Oh, man, now I got to figure it out, right? So for the radioactive decay of phosphorus 32, right? So 3215 phosphorus looks like an isotope. Oh, back to first semester general chemistry. So we got some phosphorus decaying to products. So we're going to have a stoichiometric coefficient of 1 in this case. A is very commonly 1. Well, they provide you the rate constant. It happens to be 5.61 times 10 to the minus 7th inverse seconds. Okay? Now, sometimes you'll be given half-life data. I'm going to do a separate video on half-life, all right, for that. Very common for radioactive decay to get the half-life. It's kind of fun. That'll be a neat video. All right, so if we start with 3.7 times 10 to the 18th atoms of that phosphorus and we let it decay for 125 days, how many of those phosphorus 32 atoms, or isotopes, right, atoms of that isotope, remain? That's the great thing about decay, decomposition, right? So with radioactive decay, which follows first order reaction kinetics, that's a hint. It's radioactive decay. It's probably going to be first order, right? It's just going to decay slowly over time and go bye-bye, right? Kind of fascinating stuff. If you ever get a chance to take nuclear chemistry, it's really, really neat. In grad school, I took a class, getting my PhD, I took radioisotope techniques, and I got to run a nuclear reactor at UCI. It was kind of cool. I mean, that was decades and decades ago, so I don't know if that's still functional and whatnot, but, there's, I think, 4 of us in the class, and we got to do an experiment blasting stuff with a nuclear reactor. It was so cool, man. We're sitting in there going, oh, do I feel sick? Do you feel sick? We were just fine, but you do stuff in your head, right? So again, step 1, determine the reaction order. Now, if it's provided, if it specifically says it in the problem, you're good to go, right? If it doesn't, you go, wow, poop on you, man. So I don't have concentration time data, so I can't make a plot and, see if it's a straight line or not. But I was provided the rate constant. Whenever you're provided the rate constant, right? If they don't give you units, they're evil, right? But we got units. It's inverse time. Only first order reactions have rate constants with units of inverse time. So from the units on that, we know it's first order, right? You also would know, if you remember, radioactive decay's first order. First order due to right, boom. So again, that's the first thing. I don't even attempt. I don't just grab my calculator and start going blah, 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 right? I don't want you throwing mud at the wall and hoping it sticks. I want you to know what you're doing. So every kinetic problem, the first thing, drill it into your head. Is it 0, first, or second order? Bam. Read the problem. Don't worry about the numbers. Don't worry about anything. Go, what is the reaction order from the problem? And if it's stated, great, more power to you. Step 1's easy. If not, you got to do some trick like that, right? Look at the units of K, do a plot, whatever you got to do. Okay? And we'll see how we can do that from some, we might do the video in half-life. Sometimes if you're given half-life information, you can determine what order it is. All right. Well, now that we know it's first order, we can use the integrated rate equation for first order reactions. Either that's provided for you on exams and quizzes, or your professor's going to make you memorize it. Oh, no. Right? And so we can write that equation down and plug all the data into it, which we'll do on the next board, and then solve. In this case, we're solving for how many atoms remain. So that'll be the final concentration. We're not in molarity this time. We're in just number of atoms, right? It's just amount. Which means we should have been provided every single other piece of information. You just plug it in and do the math. That's it. See if you can do it. Pause it. Write down the integrated rate equation. You could do either one of the 2 I gave you. It works either way. It doesn't really matter. I find in general, like I said, if you're solving for either the final concentration or the initial, the one where you do the logarithm of AT over A naught seems to work a little bit better. Totally up to you. Have at it. All right, my first approach, and there's several ways you can attack the mathematics from this. Perfectly fine. So I chose to use this form of the first order integrated rate equation. You could have taken the log of AT equals negative AKT minus log of A naught, or plus log of A naught. I don't have those necessarily memorized myself. Either one works. So I'm going to do this one. Now what I'm going to do is I'm going to look at what am I provided in this problem. All right, I'm solving for the number of atoms after, 125 days or something. So I'm solving for AT. I was given the initial number of atoms of that 32 phosphorus isotope atom. All right, so I know this. Check. I know the initial. I know the stoichiometric coefficient, which was 1. I was provided the rate constant. That's how I figured out it was first order from the inverse time. And I know the time elapsed, 125 days. Boop. So I've got 1, 2, 3, 4, 5 variables there, provided 4. It's just math now, right? That logarithm term makes it a little more challenging because we're going to have to take e to the x of both sides to get rid of that. That's okay. So what I'm going to do is I'm going to calculate this term over here, right? Beautiful dimensional analysis doesn't necessarily work in one nice step for kinetics, right? We're just going to get to the answer here. But I want to see where units cancel out. So I'll take my red pen of death to cancel out units. So I'm just going to leave the log of AT over A naught on this side. So negative, pull the negative sign down. A was 1 from the equation provided. The rate constant was 5.61 times 10 to the minus 7th inverse seconds. So I'm going to write seconds on the bottom there. Times the time, which is 125 days. Now notice seconds and days don't work out. So if you don't include units, you might not catch the fact that the units don't cancel for time. So I need to convert days into seconds. So 24 hours per day. I wanted to start singing a song for some reason there. I don't know what song that was, but anyway. So days cancel out. I've got 60 minutes per hour, so hours cancel out. 60 seconds per minute, so minutes cancel out. And now I've got seconds in the denominator from the rate constant, seconds in the numerator over here. All the units cancel out. That's going to be necessary because we're dealing with logarithms here, which are unitless. So boom, units are gone. These are all exact. 3 significant figures in the time, 3 significant figures in the rate constant. That number's exact, so I got 3 sig figs. So when I do all of this, I get negative 6.0588. Put my vertical dash line between the 5 and the 8 to reflect the 3 significant digits. So that's the negative AKT term. Now what you got to do is we need to isolate out A at time t. I know A initially. So I'm going to take e to the x of both sides, and that's going to cancel out the log term, leaving me just AT over A naught. And I'm going to take e to the x on this side. And then you just multiply through by the initial concentration, and you're done. So essentially, you're just going to get the initial concentration times some factor that shows how much it decays over time with the exponential term. So if you want to jump ahead of me and do that, great. But that's my first step, get that negative AKT on the right-hand side. Now let's get rid of the logarithm. I'll do that real quick. All right, follow along with me. We ended up here with the negative AKT was negative 6.0588 to the 3 sig figs. All right, so now I'm going to take, I skipped this step here. I'm going to take e to the x on both sides. So the e to the x, so the e to the log term cancels out to give you 1. So you just get AT over A naught. And I plugged in the initial concentration, I guess, 3.7 times 10 to the 18th atoms. All right. So it just wipes out the logarithm term. And then you got to take e to the x on this side. So I'll get e to the negative 6.0588. All right, pretty straightforward. That's how you get rid of the log term. And now what I want to do is get this term. So the e to the negative 6.0588, right? So I've got 2 significant digits on the right side of the decimal place there, which means I'll get 2 significant digits in my answer over here. So remember, when you take the logarithm of some factor, the number of sig figs becomes the number of, we say decimal places, but technically the number of significant digits after the decimal place. There's a term for that. I can't remember what that was, but oh yeah, mathematics, right? So the two decimal places that are significant gives me the 2 sig figs here. So 0.002337 with a vertical dash line between the 3's. So now, really, it comes down to this. I'm going to move the initial concentration over to this side. So the concentration at time t will be A naught, which is 3.7 times 10 to the 18th atoms, times this exponential decay factor, right? 0.002337, good to 2 sig figs. So 2 sig figs, 2 sig figs, I'll get 2 sig figs. Essentially, if you look at that number, that's like 0.2% or something, that term. So which means after 125 days, essentially you have about 0.23% of the initial amount left. Kind of cool. It just follows the mathematical exponential decay function there. So I get 8.646 times 10 to the 15th atoms left, good to 2 significant digits. So that does not round up. It stays as 8.6 times 10 to the 15th atoms of that phosphorus isotope we started with. So what a beautiful thing. We can use first order reaction kinetics from the integrated rate equation to be able to calculate how much of that component, that reactant, is left after a certain amount of time. Very, very useful when you're looking at, like I said, radioactive decay, carbon-14 dating, dating of like how old rocks are. I'm not going to get into details. That's a whole video in and of itself just on radioisotope dating. It's so much fun, but you'll have to take a more advanced class or do an entire chapter on nuclear chemistry. But you need to understand first order reaction kinetics to really understand radioactive decay. It's awesome, right? That you can calculate the concentration at any time, or you can say, we could have flipped this and said, okay, well, how long would it take to end up with these many atoms? And then you can calculate T. That's what we did in the zero order problem. We calculated T. This one, we calculated the concentration after a certain amount of time. So there's one more where I want to calculate the rate constant. We'll do that for the video on second order reaction kinetics, which will be next. And once we've got 0 first and second order reactions down, we've got all the integrated rate equations. And again, in my class, you don't need to derive those using calculus. I'll provide you the equation. So you can just skip that unless you are hungry for more math. But know how to do basic problems like this, how to get the reaction order, find the integrated rate equation, find all the variables provided. There should be one that's not. That's the one you're solving for, and do your math. Watch your units. You're good to go. Track your uncertainty. Life is good. But once we've got 0 first and second order done, then I'm going to look at the half-lives and show you that we can relate half-lives to the rate constants, and it's different for 0 first and second order. Woo! Let's get to the next video on second order reaction kinetics. Yeah!